This is Zhenyu Ning from Wayne State University, and today I'm here to present our paper, Ninja, towards transparent tracing and debugging on ARM platform. This paper is a joint work with my advisor, Professor Fengwei Zhang. And today my talk will cover a short introduction and some background knowledge, overview of our system, and the evaluation of our system, and finally I will conclude our work. As we all know, the malware on the mobile platform now threatens people's daily life, and how to efficiently identify this malware becomes very important. Although we already have a bunch of malware analysis systems on the ARM platform, but the evasion malware is still something that we have to pay much attention to. As the name says, the evasion malware is a kind of malware that aims to evade from the analysis. In particular, it tries to detect whether the malware analysis system is present or not. If the malware analysis system is present, the evasion malware will try to hide its malicious behavior and pretend to be something like a benign application. However, in the end user's device, normally the malware analysis system is not there, and the evasion malware will try to exhibit its malicious code and start to manipulate the user's device. The existence of the evasion malware encourages us to build a more transparent malware analysis system. Here, the transparent means that we don't want the evasion malware to detect the existence of the malware analysis system. In that case, since the evasion malware will always consider the malware analysis system is not present, so we can actually learn its malicious behavior once it starts to tamper the user's device. And in the malware analysis system, we say there may be 3 different layers. The hypervisor or emulator layer aims to visualize or we say emulate a physical machine. And on top of the hypervisor and the emulator, there is an operating system. And the operating system will provide system-level APIs for the applications running inside this operating system. And in the application layer, we may have some benign applications and also the malware. The traditional malware analysis system works inside the hypervisor or emulator. And they use the hypervisor or emulator as an isolated execution environment. Since we can introspect the memory and registers of the operating system from the hypervisor or emulator, so the malware analyzer can identify whether something malicious is happening inside the operating system. From the view of the functionality, we say this kind of architecture is pretty good. But from the view of transparency, we say not really. That's because the hypervisor or emulator will leave some detectable footprints, like some string properties, like the absence of some particular hardware components, like some additional performance slowdown. And all these footprints can be easily detected by the evasion malware. And once these footprints are detected, the evasion malware can use these footprints as the proof of the existence of the malware analysis system. And even the recent hardware-assisted visualization technique also has some artifacts on basic instruction execution semantics. To address this issue, researchers started to analyze the malware in a bare metal environment, or we say inside the operating system. They try to access the states of the malware by using some system-level APIs, or they try to modify the system-level software. And since there's no hypervisor or emulator involved in this architecture, the malware cannot split its behavior according to the detection of the hypervisor or emulator. However, as the malware analysis system is running inside the operating system, so some malware with a higher privilege, we say something like the rootkits, they can easily detect the malware analysis system or they can even manipulate the malware analysis system. In 2015, Malt introduces a new mechanism that leverages a hardware feature named system management mode in x86 architecture to create an isolated execution environment for the malware analysis system. And since the system management mode has a very high privilege, so it can access the states of the malware running inside the operating system. However, since the system management mode is not originally designed for the security purpose, so the performance overhead for the model switch, I mean the switch between the system management mode and the normal mode, is very high. And also, Malt modified some registers, but it failed to find an efficient approach to protect the modified registers. So the evasion malware, they may detect Malt by the modified registers. And also, Malt is vulnerable to the external timing attack. That means the malware can use an external timer to detect the existence of Malt. Then, how to build a really transparent malware analysis system? In our opinion, we consider that a malware analysis system should consist of an environment and an analyzer. The environment will provide the access to the states of the target malware. And the analyzer is responsible for the further analysis of these states. To achieve a transparent malware analysis system, first, we believe the environment should be isolated from the target malware. Otherwise, the target malware may be, otherwise the environment may be directly manipulated by the malware. And also, we consider the environment should exist on off-the-shelf bare metal platform. Why this? Because we believe that the environment, like hypervisor or emulator, cannot be really transparent. Due to the complexity of the hardware and the software, we consider the perfect emulation, or we say perfect visualization, is not really practical. In contrast, if the environment already exists on the OTS platform, then the malware cannot use the existence of this platform as the existence of the environment as a proof of the existence of the malware analysis system. In other words, an environment that exists in the OTS platform is naturally transparent. In regard to the analyzer, we consider it should not leave any detectable footprints like memory, like registers, like temporary files to the outside of the environment. Otherwise, the evasion malware can easily detect the analyzer. And before we actually start to talk about the architecture of our work, I would like to introduce some background of the hardware features that we use. The first hardware feature is ARM TrustZone. This technology is introduced by ARM around 2002. And this technology will divide the execution environment into a secure domain and a non-secure domain. And the hardware ensures that the non-secure domain cannot access the states of the secure domain. For example, the RAM is partitioned into secure and non-secure region. And the non-secure domain cannot access the secure memory region. And also, the interrupts are assigned into secure and non-secure group. And the non-secure domain can only be aware of the non-secure interrupt. Also, the secure sensitive registers can only be accessed in the secure domain. And even the hardware peripherals can also be configured as secure access only. In the ARMv8 architecture, other than the non-secure domain and the secure domain, the whole system is also divided into different exception levels. And different exceptions are delivered to different exception levels. From this figure, we can find out that in the non-secure domain, we have exception level 0 for normal applications, and non-secure exception level 1 for the rich operating system, and non-secure exception level 2 for the hypervisor. In the secure domain, we have secure exception level 0 for the secure applications, secure exception level 1 for the secure operating system, and a secure exception level 3 for the secure monitor. Normally, we say the secure domain has higher privilege than the non-secure domain. And also, the higher exception level has a higher privilege. So in this system, the secure exception level 3 has access to almost everything in the system. And the only way to enter the secure domain from the non-secure domain is to trigger exception level 3 exception. And if we want to return to the non-secure domain, we can use the exception return instruction, erect. And other than the TrustZone, we also use the performance unit and the embedded trace Macrocell. The performance monitor unit, or we say the QEMU, leverages a set of performance counter registers to count the occurrence of different CPU events. The events, we can say something like the CPU cycles, something like the retired instructions, something like the system calls. And the embedded trace Macrocell use a dedicated bus to trace the instructions and the data of the system. And the trace result of the trace result is outputted into the pre-allocated buffers on the chip. And both of these two features exist on ARM Cortex-A5X and ARM Cortex-A7X series CPUs. And both of these two series of CPUs are widely deployed on recent mobile devices. And one more important, both of these two features will not affect the performance of the CPU. And that's an important reason why we try to use this kind of hardware features. And in this paper, we will present a transparent malware analysis framework called Ninja. And now let's get to the overview of our system. As the other malware analysis systems, we execute the target malware in the non-secure domain and in the rich operating system. Once we want to suspend the process of the targeted malware, a secure interrupt is triggered. And the secure interrupt, or we say a secure asynchronous exception, will enforce the CPU to switch to the secure domain. The source of this secure interrupt is very broad. It can be button pressing, it can be some clock events, it can be a system call, it can be anything that can trigger an interrupt. And after the CPU is switched to the secure domain, this secure interrupt is handled by our secure interrupt handler in the secure exception level 3. And then if we want to trace the execution of the target malware, we can forward the interrupt to the trace subsystem. And then our trace subsystem can start or stop the trace according to the interrupt and the previous trace status. And we use the ETM to help our trace. Based on ETM, we implement some functionalities like instruction trace, like system call trace, and Angel API trace in the trace subsystem. And the hardware-based trace, just like we said, it will not induce any performance overhead. So it is immune to the external and internal timing attack. Similarly, if we want to debug the target malware, the secure interrupt can be forwarded to the debug subsystem. In the debug subsystem, we leverage the QEMU to implement some debug features, like the single instruction stepping, like the breakpoints, like the memory reading and write. And also, we connect the debug subsystem to a remote debugging client via a secure port. This secure port can only be detected by the secure domain. The non-secure domain cannot be aware of this port. And the analyst can send the debugging commands through this debugging port. And we use the GDB-like debugging protocol to help the analyst to introspect the memory and the registers of the target malware. In the meanwhile, as in the trace subsystem, we modified some ETM registers. And in the debug subsystem, we modified some QEMU registers. Now we want to protect these registers from being detected by the evasion malware. Oh, sorry, I missed that. After we have traced the target malware or debugged the target malware, we can use the exception return instruction to return to the non-secure domain. And if we want to protect the ETM register and the QEMU register, we use some hardware-based traps to trap the system call instruction access to the ETM and QEMU registers to the secure domain. For example, this piece of code in the non-secure domain try to access the value of the PMCR-EL0 register and test whether the last bit of this register is set. But in fact, the last bit of this register contains the sensitive information that indicates whether our PMU is enabled. And of course, we don't want to leak this kind of information. So we set the TPM bit of the MDCR-EL3 register. Once this bit is set, any system instruction access to the PMU registers will accept an EL3 exception. That means before this MRS instruction is actually executed, the CPU will automatically trigger an EL3 exception. And this EL3 exception will bring the CPU to the secure domain. Next, in the secure domain, we can analyze the current executing instruction in the normal domain. And then we will learn that the instruction in the non-secure domain is trying to save the value of the PMCR-EL0 register to the general purpose register X0. So we just store an artifactual value into the general purpose register X0. And this value will tell the non-secure domain the PMU is not enabled. Then we have to modify the value of the exception link register, which contains the exception return address, so that once we get it back to the non-secure domain, we can bypass the MRS instruction. Finally, we just use the erase instruction to resume the execution of the non-secure domain. With these actions, we can protect the PMU registers like PMCR-EL0 from being accessed by the non-secure domain. Now let's get to the evaluation. First of all, let's check the transparency of Ninja. Recall the transparency requirement we mentioned earlier. We have an environment and we have an analyzer. We have some requirement on the environment and the analyzer. In our system, Ninja uses the TrustZone as the environment, and the execution of the analyzer is inside the secure domain. Since the hardware features guarantee the isolation of the non-secure domain and the secure domain, so we can say that our environment is isolated. Also, we know that the TrustZone technology has been widely deployed in recent mobile devices. So we say it already exists on the OPTS platform. In regard to the analyzer, we use technicals like just we mentioned, the hardware-based traps, and also some software-based memory mapping redirection to protect the PMU and ETM registers. Although the hardware-based approach can provide a very good protection, but the software-based approach may not fully protect these registers. So we say our analyzer is not fully transparent. That means Ninja is not perfect. We also have a transparent issue. Learn from the evolution of the malware analysis system, we will argue that the hardware-based approach may provide better transparency than the software-based approach. And we may need additional hardware support to build a transparent, fully transparent malware analysis system. And also, since we consider the hardware-based trace subsystem is immune to the timing attack, we want to evaluate the performance of our trace subsystem. Our test bed is the ARM Juno V1 development board. And this board contains a dual-core 800 MHz Cortex-A57 cluster and a quad-core 700 MHz Cortex-A53 cluster. And we built the software part of the Ninja based on ARM-trusted firmware. We say the ATF version 1.1 and Android 5.1.1. Firstly, we use the Zhenyu multiple precision arithmetic library to calculate 1 million digits of pi in different situations and compare the time consumption of different configuration. From this table, we can find that the time consumption of node tracing, of the instruction tracing, and the system call tracing, they are very similar. This also proves that the hardware-based trace does not affect the performance. However, in the Android API tracing, because we have to use some software-based approach to bridge the semantic gap, so it brings additional overhead. It is about 17 times slowdown. And also, we use the CF bench application on the Android platform to manage the performance scores. The result also shows that the hardware-based trace does not affect the performance. And the software-based approach will introduce about 4 times to 154 times slowdown. In regard to the time consumption of the domain switch, we also manage it in different situations. If we disable both the ARM-trusted firmware and the Ninja, we just use the TrustZone to finish the domain switch. Then it requires only 0.007 microseconds to switch between the secure domain and the non-secure domain. And if we enable the ARM-trusted firmware, the time is increased to 0.2202 microseconds. And if we enable both ARM-trusted firmware and Ninja, then it requires about 0.342 microseconds to finish the domain switching. Note that the mount requires about 11.72 microseconds to switch between the system management mode and the normal mode. That means the domain switch of the TrustZone is more than 1,600 times faster than the model switch of the system management mode. And even in the worst case, we enable both the ARM-trusted firmware and Ninja. We are still about 34 times faster than mount. In conclusion, in this paper, we present Ninja, a towards transparent malware analysis framework on ARM platform. It can transparently trace and debug the target application with some hardware features like TrustZone, like QEMU and ETM. And our hardware-assisted trace subsystem is immune to any kind of timing attack. Thanks for your attention, and I'm happy to take any questions.
Okay, so again, we have time for a few questions.
Hi, Stefan Sorio, Macrocell Research. Very nice talk. I really enjoyed it. I have a clarifying question. You made this comment that you could have some insights into what additional hardware you might want to have to assist in your project. Can you comment more on that? So what would be sort of other hardware extension you could use?
For example, just now we mentioned our software-based memory mapping redirection technology cannot fully protect the registers because the registers is mapped into some memory region, and the software-based approach cannot provide a good protection to this memory region. But in ARM, we have some hardware like the TrustZone address space controller. Right. With that piece of hardware, we can protect the RAM of the system.
Right.
But the register we mentioned is not located on the RAM. So we cannot use the TrustZone address space controller to protect the registers. But if we have some additional hardware can provide some functionality like the TrustZone address space controller to the hardware registers, maybe we can provide a better capability.
I see. Okay, thank you.
Thank you.
Okay, then I have another question about the limitations of Ninja. So because the title also states that it's towards
Yes.
transparent analysis, and I can imagine that a malware could also try to change the semantics, because to a certain extent you rely on some information that you want to recover. So what do you think what a malware could do to evade Ninja?
Currently, because just like we mentioned, the registers, we cannot fully protect it, and also another possible evasion technology is because we use the QEMU and the ETM, and these two hardware components is available in the operating system level. So if the malware intentionally to start the QEMU or to start the ETM, then maybe they can detect us. To prevent this kind of attack, we may need some dedicated, because it is a piece of hardware. If we have some dedicated QEMU, some dedicated ETM, then we are good.
Okay, and if we don't have additional questions, let's thank the speaker again.
Thank you.